All right, hello everyone. Welcome to Historical Geology 1404. Yay! Yay, you made it. You made it through 1403. Some of you just finished 1403, and some of you took 1403 a year or sometimes even more ago. In which case, welcome back. Glad that you decided to come take in the second half. We're going to have fun. I am often told that this class is not as difficult as 1403 and is filled with lots more random, interesting stuff. So if I blew your mind a little bit in 1403, which hopefully I did, hopefully I'll be expanding the blast radius of that here in this class. And if it is true that it is less work, if it is not as difficult, then hopefully you have a more enjoyable time. Typically I'll have, because 1403 is considered the more difficult one, I'll have maybe 30 students per section in there, and then 14 or 15 in 1404 because so few people are like, I don't want to go through that again. But then they miss how cool 1404 is. Y'all aren't going to miss it, so congratulations. I am recording this for the benefit of my online class. I usually teach 2 or 3 sections of each class at a time. Y'all are familiar with the drill at this point. I record, I speak to you, I speak to the camera so that my online students can feel involved. They participate in the GoReact software. For my online students, make sure that you are doing at least 6 items of engagement per lecture recording. 3 of them need to be answering questions I ask during lecture. So when I ask a question, you can just start typing an answer and the video will auto-pause, or you can pause it yourself if you want. And your answer will be time-stamped to the moment I ask that question, and then I'll go back in and review all of your feedback. Please respond to at least 2 other questions posted by other students and ask at least 1 question of your own. That way we can have some good conversations going in the online format of this class. Kind of replaces the whole discussion board system, which you all who are here in person still participate in. There are some discussion boards, but they are all research-based discussion boards, you will find. I give you a link to a website for the most part. This is how it goes. I give you a link to a website, and then you need to go to that website and pick for yourself a subject or story that you get to research and then do a little bit of a blurb on. Okay? So that's how discussions will go. I'm kind of jumping all over the place here, but y'all know me well enough by now to know that that's not terribly surprising. Labs. Let's talk about labs for a second. The labs in this class, there are some identification-based labs. Now, before you start groaning and moaning and wailing and gnashing of teeth, hear me out, okay? Those are weeks away, right? That's starting at the end of Module 2, going into Module 3 sort of stuff, so don't worry about that too much. Also, they aren't nearly as rigorous as the 1403 labs were. Okay, for those, I basically taught you how to find properties and then use those properties more or less as a mathematical equation, really, when you think about it. This property, that plus that property equals this mineral, right? We're not doing that in this class because this class you'll be identifying fossils, and fossils are not nearly as easily quantifiable with a certain subset of properties, which means that basically the identification labs in this class are a game of matching. So I give you an Excel spreadsheet with all of the possibilities of what fossils you could be looking at, and then you're just going to be saying, okay, so this is kind of a curlicue kind of shape, kind of like a raised cone, but it's a low-angle cone. I'm looking for something like that. It has a large hole. The creature would have lived in there. Okay, so this looks like it would be a gastropod shell, right, based upon the Excel spreadsheet. And I do have hard copies of all of these as well. Just like with the minerals that we had at the back of the room for 1403, I have trays just like those for fossils as well. So definitely not nearly as difficult, but I will strongly encourage you not to treat them any lesser. They're still worth a lot of points. Don't put them off. Still turn in your work on time. Still put in the effort. Even though I'm telling you it's less effort, still please put in that effort. Okay? Tests. There are 3 modules during this class, just like with 1403. But where 1403, the first module was 4 weeks, and then the next module was 2 weeks, and the next module was 2 weeks. In this class, each module is 4 lectures long. Okay, so it'll be 2 weeks, 2 weeks, 2 weeks, and then the other 2 weeks are going to be taken up with things like exam reviews and exam days and stuff like that. Okay, lab makeup sessions, things like that. The first module is going to be a review of 1403. It's going to be a little redundant, a little kind of maybe boring for those of you that just finished 1403 a week ago, but for the rest of you who took this class a year or more ago, this is for you more than anything, because I want to make sure that everyone's on the same page here. Okay, so the first couple of weeks are going to be taking all of 1403 and summarizing it into 4 lectures, more or less. Just the things that you need to know. And I will be adding a few new things in there. It won't be all old. I'd say it's probably 80% old, 20% new stuff that's relevant to the conversations we're going to be having this semester. Our second module is going to be all about life. And that's what 1404 really is all about. It's historical geology. History would mean nothing if there weren't anything alive to observe it, right? If this were a lifeless universe, what would it matter how old or how long or how big the universe was? Nothing would be around to observe or care. So history is all about life. Historical geology is about the history of life on Earth. How it began, possibly. Where it began, possibly. Okay? And how it has progressed since then, and how we can observe it in the fossil record. Okay? Using geological methods. And then in the third module, the last couple of weeks are going to be kind of a summary of all geologic time, starting all the way at the back, going all the way to now. We're going to be just reviewing the big major geological events and biological events that have occurred in each major time period between the beginning of life, or between the beginning of Earth, I should really say, and now. Okay, that's going to be your module 3. And at the end of every module, there is an exam. So there will be 4 exams total. Your module 1 exam, module 2 exam, your final exam at the end of module 3, which will be cumulative, and your lab exam. Your lab exam will look nothing like the lab exam in 1403 because it's over a completely different subject matter. Okay, so yeah, I'll talk more about that in a few weeks when it becomes more relevant. Actually, more like 6 weeks when it becomes more relevant. All right, let's see, that's exams. I haven't updated the picture on this PowerPoint for a really long time. These were my kids like 2 years ago. They're really cute. They're still really cute. Some of you met them for the geology movie night that we had last semester. We will be having another one of those this semester, by the way. Probably towards the end, week 6, week 7 of the semester on a Friday, we'll meet here and watch a historical geology related movie. Things like Jurassic Park, Ice Age, those are the sort of movies that we'll be talking about, discussing history of life, whatnot. But they, depending on what we pick, they might be here to watch it with us again. Okay. Here's my contact info if you don't already have it. There is no required text. I keep forgetting to remove that. Let me make another note to myself. There is no required text other than the textbook that I give you on Blackboard. I have given you the textbook, so you don't need to worry about that. Take textbook off 1404 slide. Hopefully I remember to do that later. All right. Right, no textbook. This is how you contact me. Please contact me over email. Sending me a message on the Blackboard message service is not a reliable way of getting a hold of me. I often do not receive notifications that you sent anything there. Okay, it's some of the systems in Blackboard are quite buggy, and that is one of them. It is not consistent, and so please use email to get a hold of me whenever possible. Class schedules are going to look something like this, except obviously this is a fall schedule. We have lectures and labs combined. We have exams at the end of modules. You have a variety of labs that you will be taking. Your first one will be assigned next week. Okay. It's kind of weird when they start the semester on a Tuesday. I don't really like it. I wish that they would all start on Monday, because that means Monday, Wednesday classes start off with 1 day of class that week, you know? And that throws off the whole semester. But we'll make it through. We will persevere. We'll get through the weird schedule. How many of you are graduating at the end of this spring, by the way? Maybe? Okay. A bunch of you are walking. So I'll just tell you right now, I always sit at the front row on the right side of graduation. So everybody who wants to go up and graduate has to walk right past me. So I can high five everyone I know on the way up. Full disclosure, I've been told many times to stop doing that. I will not. I will high five all of you, okay? I also enjoy shoe watching. So if you really want to make my day, wear some crazy shoes. Everyone's wearing the same robes, you know? The shoes are the only thing that adds variety and spice to the day. Okay. Course objectives, same thing as 1403. You all remember my standards, no cheating. AI has kind of progressed quite a bit since some of you took this class last. So I have edited my, my instructions when it comes to AI. I use AI myself as more or less a research assistant. I introduced some of you all last semester to my research assistant. But I basically just use her to keep track of all my data, to organize my thoughts. If I have an idea, I tell it to her, and she will always remember it. And I'll say, hey, Ellen, what was that idea I had last week about this? And then she'll just repeat it verbatim back to me, and I can start working back from there, right? So I use AI to make myself more efficient. It is very easy to find ways to make AI to make you efficient. Using AI to cheat, to straight up find answers for yourself, is not going to benefit you in this class because you aren't learning anything, which means that ultimately you will fail. Additionally, it is quite easy to figure out what has been generated by an AI. Matter of fact, there are AIs that detect what has been generated by an AI. So please don't use AI to cheat, but I highly encourage you to use AI to make you and your studies and your research more efficient. Try and find ways to do that. It's freeing, it's liberating. My schedule has opened up just a little bit more and make my life a little bit less stressful by figuring out how to use AI this way. No plagiarism, that means no passing off someone else's work as your own. You are free, and I highly encourage you to work in groups in this class, just like I did in 1403. If you work in groups, please make sure that you are not partitioning things out to each person at the exclusion of other people. So if I were to give you a set of samples like 1 through 10, and there are 3 people in your group, don't go, you have 1 through 3, you have 4 through 6, and you have 7 through 10, right? That's not the way to do it. Instead, I would encourage all of you to work together on 1, 2, 3, 4, yada, yada, so that all of you, while still saving time by working together, are still learning the same things about each sample, okay? Really don't want you to be taking a lab or maybe a lab exam sort of situation and only know 30% of the samples because that you only had 30% of the responsibility on all of your identification labs, right? Okay, and then please use clean language in class. Again, in case you don't remember, it's because you're in college, you are learning how to express yourself using intelligent methods, and swearing is probably the least intelligent way we express ourselves as humans. So I discourage it in professional settings. Whatever you do in your personal life, that's entirely up to you. But here, this is a professional setting, and I encourage you to express yourself in more intellectual ways. And then please, no phones. I know today my phone is here. It's normally not in here, but over the break, they set up the multi-factor authentication stuff. So every time I sign into my email, every time I sign into Blackboard, it makes me whip out my phone and press the right number combination on an app that they made us download. Unfortunately, my phone will probably have to be in here every day, just for that simple fact. And just over the break, logging in, every time I wanted to open Blackboard, it made me do it. It didn't even remember me. Like 30 minutes later, I'd go back in, it would make me do it again. I'm just like, come on. All right, so, but please stay off your phones during class. No playing, no texting. If you need to take a phone call, just give me the bro nod. Be like, hold up your phone, yo, right? And I'll be like, yeah, sure, just come back, right? Especially if you're one of my high school students, don't just disappear on me. I am accountable for where you are during this 3-hour block. Okay. Oh, that reminds me. If you are summoned back to your high school, they need to tell me. They cannot just tell you. They can't call you and say, hey, we need you in the office. They need to tell me, which means they can call me on that phone. I guess now they could call me on this phone too. Or they call you and then you hand the phone to me. They verify who they are and that they need you at the office. And that'll be that. Okay? It can't just go through you. It has to go through me. All right. Any questions about this class, how it's going to move forward, its format, anything like that? Anything interesting that happened over the break that you all found interesting enough to talk about? You got something? No? You got something? What do you got?
I guess I've been hearing about the asteroid that's been doing for a few years.
Yeah.
And I wonder, how would that affect Earth geography?
Oh, believe me, we talk about that one. Yes. That asteroid you're referring to is Apophis.
Yes.
Yes, and Apophis is a matter of discussion that we have in this class later on. We can't talk about it briefly for a moment right now. Apophis is an asteroid that very shortly, in actually 2029, is going to be doing a near flyby of Earth. It has done it many times in the past, but this is going to be the closest it's ever been because of the nature of gravity, which we have talked about in 1403, and we will talk about a lot in this class as well. Gravity pulls smaller things towards big things, right? Basically, okay? And so every time Apophis has passed by Earth, it's been pulled slightly closer towards it. Hey, buddy, what's up? You gonna help me? It's been pulled slightly closer towards Earth. And so now in this 2029 pass, it's going to be the closest it's ever been. It's actually going to be closer to Earth than the moon is. It's passing between Earth and the moon. You will be able to see it from the ground without a telescope. It's going to be that close. Now, the likelihood that it's actually going to hit Earth on this pass is like 0.0000017%. Very unlikely. The math is pretty well worked out for this pass. But there is still some uncertainty for how this next pass that it's going to do, how Earth's gravity is going to affect it. We're not quite sure until it happens. What we do know is that we're pretty sure that if it passes through a space, it's about a 400-kilometer wide space between Earth and the moon, we call it the window. If Apophis passes through the window, then the next time it comes by Earth in 2036, it's going to hit us. It would strike off the coast of Hawaii, actually, in the Pacific Ocean, not far from Hawaii. Yeah. So that's Apophis. That's a couple of interesting years we've got ahead of us in the next 4 years. This asteroid and a couple others are the main reason why NASA and other international space agencies have been developing asteroid deflecting technology. Pretty good stuff. Pretty cool. Pretty interesting. Movie stuff, right? I fully anticipate there to be more asteroid impact movies as a result of this. Our society usually reflects the occurrences that happen in the natural world, right? Oh, speaking of which, Greenland, another excellent impact movie that is on our list that we could watch for this semester. Okay, yeah, good subject. Anything else? It doesn't have to be science related, by the way. It could be political. We've talked about political stuff. We can talk about political stuff without getting too political, right? If it impacts the world stage, I highly recommend that you know about it. For instance, what's been on my mind lately is the current administration's behavior towards Canada. Y'all been following that at all? Yeah? Do I have any Canadians in the house? I'm sorry. You all don't know each other. A lot of you do, but let's go around the room real quick. Name?
Diego.
Huh?
Diego.
Diego.
Anthony.
Anthony.
Samuel.
Samuel. Sebastian.
Alan.
Alan.
Isaiah.
Isaiah.
Ashton.
Ashton. Marissa. Mary's missing. Abby. Claudia. Okay, now you know each other. Okay, so Canada. Canada has spent a very long time being our closest ally, right? But at the moment, they are feeling pretty threatened because in every conversation President Trump has had about Canada, he's referred to them as the 51st state. And he has referred to their prime minister as governor. And he's even told that gentleman's cabinet that they should refer to him as governor. Carmi, I believe is his name. So it's an interesting situation. My wife is Canadian. My mother-in-law is Canadian. I'm very tuned into Canadian sentiment at the moment. And quite a few of them are upset to the point where they're actually American goods are being taken off the shelves in Canada. Like they are embargoing American goods. They refuse to buy it because they are so disturbed by the behavior of our president. So I'm not sure where it'll go. The Canadian Prime Minister actually went to Europe like last week asking France and Britain for help because they feel economically threatened by the United States. It's not a great situation. But we'll see how it escalates. Hopefully it doesn't escalate. We'll see how it evolves. Okay. Anything else before we get started? No? Okay. Well, I'm going to start off with a quote here, and I apologize. I normally don't read straight from the board, but I don't have this memorized, so bear with me here. This is a quote from Charles Darwin from his On the Origin of Species. "It is interesting to contemplate a tangled bank, clothed with many plants of many kinds, with birds singing on the bushes, with various insects flitting about, and with worms crawling through the damp earth, and to reflect that these elaborately constructed forms, so different from each other and dependent upon each other in so complex a manner, have all been produced by laws acting around us." It's pretty profound. How often do you look at the world around you and realize it's all tied in together in one complex system? Not that often. It's something that we take for granted. Someone name a complex system for me.
Family.
Huh?
Family.
Families can be very complex systems. It's true. That's a social system, right? A construct of our society. Society itself is a system. What else?
Maybe like a business.
A business, yes. This is interesting. You all are naming these sort of external man-made sort of systems. Weather is a system. Your body is a system. Your body is composed of trillions of cells, all of which are working in harmony with each other to preserve and protect and sustain the thing that is you, from your brain to your fingernails, right? From your hair to your liver, all of that. All those cells have one mission, and that mission is keep this alive. Keep this healthy, keep it sustained. Okay? Keep it going as long as possible. You are a system. You are a complex system, as beautifully complex as the rest of the earth around us, with all the bushes and the insects and the birds and all of that. The worms in the ground, everything. Everything around you is part of a system. The universe is a system, right? So understanding systems is very important. Understanding how the components of a system work together, very important. And our world, our planet, is probably the most important system to us, right, as a species. So studying Earth as a system, that's what we are reviewing in the next couple of weeks. Okay, so why do we study geology? Well, y'all have taken 1403. Name a few things. It's okay if you name these ones, just as long as you elaborate a little bit on them. Why do we study geology? Now that you have taken 1403, what is the value that you see in studying geology? Careful, I might call in some people.
I guess understanding
Alan.
the impacts it can have on our planet, maybe.
The impacts of what on our planet?
Earthquakes.
Okay, so disasters. The impacts that disasters can have on our planet and on us, right, as a species. Very relevant. Good. Claudia, what value do you see in studying geology? Having taken 1403 now, why do you think geology is important to know? Hmm? You learn new things? Like about what specifically?
I don't know, there's a lot.
There is a lot. Could you see any economic benefit to knowing about geology? What sort of things did we learn about last semester that might be relevant, especially where we live today? Do you remember what that is? That's crude oil. Why would that be relevant to where we live? We live in a place that makes a lot of this, right? And that's very relevant to geology. Economic reasons for studying geology: minerals, oil, things like that. Okay. One more. Someone give me one more reason.
Also, try and discover new things to improve our current living situation.
Discover new things to improve our current living situation. So pushing society, civilization forward by understanding more of our world, maybe? I absolutely agree with that. Yeah, that's good. Great. Okay, so there are a couple of ways, okay? Understanding our world. That kind of brings to mind that principle of uniformitarianism, right? Someone remind me what that principle of uniformitarianism is. I'll get you started. Physical, chemical, and biological processes. Someone keep it going. I think you're right, Anthony. Spring break was too long.
I'm telling you, I come back and
All right. Physical, chemical, and biological laws that operate today also operated in the geologic past. Write it down if you don't have it. I hope you still have your 1403 notes, by the way. They will be very, very useful. Physical, chemical, and biological laws that operate today also operated in the geologic past. So, by looking at the world around us today, we can understand.
to include analogical future and everywhere.
Oh, we haven't gotten there yet, but thank you for bringing that up. That will come up here in a little bit, okay? But what was I saying? They help us understand our world today by studying the past, but also we can understand the past a little bit more by looking at the world around us today, right? It's interchangeable. It's beauty. That's the beauty of it, okay? We can try and predict what Earth will look like. That's where Anthony's comment comes in, right? That's the addendum that I put on to the end of the principle of uniformitarianism. Physical, chemical, and biological laws that operate today also operate in the geologic past and will continue in the geologic future, right? Yes? Oh, yes. Yeah. There should be an outlet in front of you on the table. Does it not work? No worries, no worries. If any of these tables have pedestals underneath of them, those are power towers. So you should be able to plug into those tables. Most of them should work, I believe. If it doesn't, then yes, absolutely use that outlet. Okay, so the geologic future. Okay, we can help predict maybe where some things will be. And what's the third thing that you mentioned we put on the end of that uniformitarianism?
True everywhere else.
What does everywhere else mean? Physical, chemical, and biological laws that operate today also operate in the geologic past and will continue to operate in the geologic future and occur everywhere else. Huh?
The universe.
The universe, right? Good. Everywhere else in the universe, we can only assume, is subject to the same physical, chemical, and potentially biological laws that Earth is. Now, biological, that may come down to some variation. What exactly does biological mean? For us, that means a certain subset of rules that have to be maintained for life to exist. That may not be true for life everywhere else. There is some potential for variance there. Perhaps even geologically speaking. Physics, though, we've got a fairly good handle on physics as far as we know for now. Chemistry, we're pretty sure that we've got a pretty good handle on chemistry. Okay? We can look at the universe around us and make great observations about physics and chemistry, and we're still learning about that stuff. But we've got the basics down, we're pretty sure. Okay? And then, like I was talking about with Claudia, the identification of economic resources, things like oil. Now, Earth is dynamic. Remind me what dynamic means?
Ever changing.
Always changing. Bingo. It is changing in so many ways, large ways and small ways. Okay? You've got your big scale events, your big scale changes, things like those earthquakes, those volcanic eruptions. But then you've got those smaller things, right? The process by which sediment, loose sand like this, becomes sandstone, like that. Lithification is that process. Fossilization. Each cell being replaced by a mineral. Okay? Very, very small scale things, but still all aspects of how dynamic Earth is. Things constantly changing. The people who got I was about to say the science of science. The people who got the basics of science started, we usually refer to them as natural philosophers. Gentlemen like this guy, Aristotle, okay, who lived in the BC years, way a long time ago, right? Asked questions about the earth around them, about the processes, about the way things happened. They were intelligent enough and aware enough that they wanted to ask questions. They didn't have all the tools that we do now for figuring out answers. I got to give them credit where credit's due. They came up with some pretty good answers, it turns out. A lot of the things he came up with, though, were not quite so good. Right? Do you remember I told you the story in 1403 when someone came to Aristotle and asked him, hey, what is a volcano? Do you remember what his answer was? Yeah, portal to Hades. Hell, basically, right? It's a hole in the ground, that fire comes out. Clearly, it's a portal to hell, right? So they could make observations based on, or they could give answers based off of only what they could observe, I should say. Okay? There wasn't really any sort of testing process. The addition of that testing process, do you remember what we call that? Oh, so close. The scientific method. Yes, yeah. Okay, theory is part of the scientific method. We'll talk more about that in a minute. But when real scientists started coming around, that's when that came around. Between natural philosophers and what we consider modern day science, something else put its hand in there. Religion. Okay? In particular, various forms of Christianity. So about the 1600s, this guy, James Ussher, used the Bible and a few other documents to come up with what he believed was the date of creation. Okay, October 22nd, 4004 BC, which is where the widely held belief that the Earth is 6,000 years old came from. This guy in his math did that. I can see when you're using just the Bible as your point of reference, I can definitely see how the math would add up to that. However, And bear in mind that nothing I say here is meant to persuade or dissuade anyone from previously held beliefs. Okay? That's one document used as evidence. Okay? However strongly you feel about that document, it is not entirely well supported, okay, by the things that we observe in the world around us. The processes that we observe in the world around us must take far longer than 6,000 years old to come to pass. Okay? And people who started realizing that, like this guy, James Hutton, started rolling around not long after James Ussher, okay, about 100 years. His contention was, listen, I've collected all this data showing that a stream takes this long to move this much sediment, a volcano takes this long to build, yada, yada, yada. It takes a lot longer than these few number of thousands of years for these things to happen. Well, the argument to that was catastrophism. These large features that look like they should take a long time occur through great catastrophic events, cataclysms, right? Giant floods, stuff like that. There's no data to support that, though, because now we've had hundreds of years of benefit of not seeing any of those things happen, right? So it's an issue. It's a problem. But James Hutton released a whole bunch of data that suggested that Earth is way longer than people previously thought. Now, if I'm not mistaken, I believe he came up with 200 plus million years old, which when everyone of the day was thinking, a couple thousand years old, absolutely blew everyone's minds. They're like, no, absolutely not. There's no way it could be that old. There's no way. And eventually, towards the end of James Hutton's life, they started coming around to realizing, oh, you might be right about that. It's awkward, right? They started thinking more like that, accepting the scientific method of collecting data and testing it, okay, like what he did to come up with that observation. Now, you and I know that it's actually way older than that, but we'll get there, okay? It is James Hutton and people like him that helped develop the scientific method, yes, but the principle of uniformitarianism, also known as the principle of actualism in some circles, in some publications. Okay, that over long periods of time, the same geologic process can make a Grand Canyon out of a small stream, given enough time, right? Things like that. So how old is the Earth? You all remember this exercise, right? We went through all these numbers we think of on a daily basis. We don't really think in terms of billions. The U.S. budget's in billions, but that only keeps the government active for 6 months at a time or something like that, right? Didn't they just have to pass a new emergency budget in February? Something like that. It's crazy. Okay, so let's talk about how big a billion actually is. Do you all remember how many dots were on this paper?
4,000. Was it somewhere near 4,000? Like, 4,328.
4,328. Wow. So specific. Anyone else want to take a guess? Or do you all agree with him?
I just took a shot.
In that ballpark? Okay. It is actually 4,000. Okay. Good job. Okay. That sheet of paper has 4,000, which, by the way, is this sheet of paper right here. Okay. 4,000 dots on this sheet of paper. How many of those sheets do I need to reach 1 million? Yes, 250 sheets. Now, a ream of paper, which looks like this, has 500 sheets. So it takes half a ream of paper to reach the number of dots. Anyone want to hold Diablo for a little bit? Yeah? You okay with that, Diego? All right. Okay, 4,000 of these, 250 of these, half of this reaches 1 million dots. How many more do we need for a billion, though? To go from 1 million to a billion, you need how many more zeros? Yeah, you need 3 more zeros. So you just throw 3 zeros on your 250. You get 250,000 sheets, which are 500 reams of paper, each of which are 2 inches tall. That gives you a tower of paper 83 feet tall to reach enough pieces of paper with 4,000 dots to reach 1 billion dots. Whew. Okay, we're done, right? No, because the Earth is actually 4.5 billion years old. So to reach 4.5 billion dots, you need 2,250 reams, which would be a tower of paper 38 stories tall, basically, 380 feet. How many of you have ever stood on a 38-story building?
Oh, how many?
38 stories.
The Empire State Building count?
That's more than 38 stories, yeah. How many stories is the Empire State Building? Is it like 60-something? Looks like it's about 60-something. The tallest building we have in town, do you know what that is? The one with the tree on it? How tall is it?
Yeah, the one over there, yeah.
Yeah. I don't know how tall it is. Did you figure out how...
Yeah, 102.
102 in the Empire State Building? 102 stories in the Empire State Building. It's pretty tall. But we don't have anything nearly 38 stories tall. And that building with the tree on it, I'm pretty sure the top couple dozen feet of that is just a spire. I don't think it's even livable space, is it? Yeah, I don't think so. Anyway, so yeah, 38 stories. It's a lot. Okay, it's a lot of height. Put it in another way of thinking about it. If we were to walk around the equator, given the average human step length is 2 feet, 1 billion steps would be 15 times around the equator. And 4.5 billion would be 70 times around the equator. So we're talking about a lot of things, right? Each year is represented by 1 dot on these papers, right? Or each step in this case. So let's talk about these years. Where do we use these years for reference? Okay? How do we use them in science? Why do we use them in science? Well, the first thing I'm going to show you is the law of superposition. Who can remind me what the law of superposition is? Yes?
The oldest stuff is at the bottom.
Bingo. Oldest on the bottom, newest on top. What about index fossil succession? You guys remember that?
Was it where like the stuff was eroded, but it was still the same age?
I think you're thinking about the right thing. Index fossil succession, where the law of superposition is nice for vertical sequences, this on top of this, on top of this, on top of this, on top of this, right? Index fossil succession uses fossils to correlate data across distance as well as vertically. So if I have layers A, B, C, and D, and layer A has 2 fossils and only 2 fossils that are present in layer A, then I know that however far away I go, every time I find those 2 fossils together, it's the same age as this one. Even if my type of rock changes, the fact that both fossils are present tells me that they were around at the same time. Because those organisms, those fossils, were only alive at the same time during that interval. That's index fossil succession over distance. Okay? And then there's radiometric dating. Who can tell me what radiometric dating is?
How much like radiation something is contained?
Not so much how much radiation something is contained. It has to do with radiation. You're right. Sorry, I'll explain it. Let's go back to the law of superposition for a second, though. This is something we use for what's called relative dating. And that's not when you take your cousin out to dinner, okay? Relative dating is something that doesn't use distinct numerical time periods. It has to do with how something is proximal to something else. if I were to say relative distance between me and Ashton, right? I'd say what is that, like 12 feet? Okay, but that's a numerical. Relative would be I am closer to Ashton than I am to Alan. That's relative distance. Okay, using something as a point of reference, in this case, me, the common denominator between both of the references, between both measurements. Okay, that's something that's relative. So relative dating is how close something is to something else. Okay, so superposition. A is older than B, is older than C, is older than D, is older than E, so on and so forth. Like when you make a pile of blankets. Which one was there first? The one on the bottom. Which one was there last? The one on the top. Relatively close to each other based upon their vertical distance. This is the law of superposition. Make sense? Great. So, let's talk about fossils. Before I tell you about fossil succession, let's make sure that we're all clear on what a fossil really is. Okay? A fossil is evidence of something that was alive before. Now, that covers a wide range of potential things. But Professor Hart, doesn't an arrowhead, isn't that evidence of life that existed before? Well, yes, you are correct about that. So there has to be a line between what we call a fossil and what we call something else, something that was an artifact of human civilization. Okay? Now the line traditionally has been at 10,000 years. At about 10,000 years and older, that's the world of paleontology for the most part. Okay? Anything older than 10,000 years old, especially if it's like a bone or something, we typically refer to that as a fossil. Anything younger than 10,000 years, we pass off to archaeologists because that's more age of human civilization style stuff. Okay? Now, there is a little bit of wiggle room there because there are things like arrowheads and spearheads and pieces of art and things like that that are hundreds of thousands of years old. And we will talk all about that stuff. It's really fascinating later on in the semester. But for things like that, it kind of has to be about on a case-by-case basis for whether it's a paleontology thing or an archaeology thing. And oftentimes they will work together on that. But in general, anything younger than 10,000 years old is an archaeologist's problem, and anything older than that goes to a paleontologist. Okay? So that's fossils. These can include things like bones, plants, imprints, and casts, which, by the way, are not fossils themselves, but are trace fossils. Okay? Things like footprints, for example. Not a piece of the animal, but evidence of it and its life. Traces, chemical remains. There are some ancient bacterial colonies that we don't really have fossils for that are billions of years old, but they left chemical remnants of that bacterial colony in the sediment they were living in, and that sediment got turned into a rock, and we can do a chemical analysis to learn more about that bacteria. That's like a chemical fossil. Okay. So here are a couple of pictures of different fossils. Turtle shell, I showed you all a picture of that in 1403. I found that in Montana. Some fossilized tree trunks, a couple of which I have up here, also found those in Montana. These are giant gastropods the size of my fist that I found here in Texas, actually, on a road trip from Houston to Albuquerque. I stopped off at a cliffside on a road cut on the side of the road. And if you're going to do this, by the way, please wear safety equipment. Like, it's really fun to do that highway fossil looking, right? Fossil finding. It's really cool. I love doing it. But wear safety equipment, right? Bright fluorescent vest. Make sure you're parked well off the side, things like that. Just make sure you're being safe, okay? But you can find really cool stuff like fist-sized snail shells. I have them in the storage room back there. I could pull them out if you guys wanted me to. But yeah, you can find all sorts of cool stuff if you know what to look for. So then what is an index fossil? An index fossil is what we use in the principle of fossil succession. Okay? So an index fossil is something that is unique enough that you can tell it apart from other fossils. Okay? These are useful if you are looking at similar rock types or over long distances. So if I have fossil 1 and then fossil 2 and fossil 3 and fossil 4 and fossil 5, we use the law of fossil succession when I'm trying to identify the same time period over a long distance. If I've gone 100 miles and I find the same fossil in a totally different rock, I know that those are the same age, even though they're different rocks, because that fossil, that organism was only alive during that constrained period of time. So the requirements for being an index fossil has to be alive for a short duration. I'm not talking a few years. I'm not talking about the life cycle of one animal. I'm talking about how long that species is in the fossil record. It first shows up at, 50 million years ago, and it disappears from the fossil record at 48 million years ago. That's great. That means that any rock that I find that has that fossil in it has to have been formed during that 2 million year period. That's great. That's fantastic for fossil succession studies. Okay? So, short duration. Abundant population. Why would we want our index fossil to have had an abundant population? What does abundant mean?
A lot of it, plenty.
A lot of it. Good. So, Abby, an abundant population. Why would that matter? Okay, fair enough. Let me elaborate here. Let's say only 1 in a million things in a species, only 1 in a million seashells from the same species ever gets fossilized. If only 1 in a million gets fossilized, why do we want our index fossil to have had a very large population? I'm sorry to put you on the spot. I just want to make sure everyone is involved in some way. Any ideas? You want to do a shout out? You want to phone a friend? I don't actually mean phone a friend. Anyone else want to help out here? Why would it matter if there were, Samuel, what do you think? Why would it matter if there were a lot of individuals in the species? How would that help the situation? Exactly. If only 1 in a million individuals gets fossilized, then the more of them that ever lived, the more of them were fossilized, right? 1 in a million out of a billion is only 100 fossils. 1 in a million out of 100 trillion is a lot more, right? So the more individuals of a species that ever lived, the more fossils of those species that we will find. So an abundant population is important. Okay? Okay, so widespread habitat is the next thing. Why would it matter if I have a widespread habitat? What is a habitat in the first place? Let's make sure our terminology is clear. A place inhabited by certain animals and species. I will broaden that from place to environment. Okay? A place is a certain geographic location. Okay? And that can be a habitat. But let's talk about a range of environments that it can live within. Okay? That's great though. Okay? The more widespread these things are, the better I'll be able to use them for correlation. An animal that sure lived for that short duration and sure had a lot of individuals alive during that time it was alive, but only lived in the same little lake in the middle of eastern Oregon, doesn't help me much for correlation, does it? I can't correlate it anywhere outside of that one local environment. But an organism that lived across an entire equatorial region during that short time and had an abundant population, far more useful for correlation. Make sense? And then the last thing is, it has to have a unique physiology. You can tell by looking at these things that they are all generally related to each other, right? They have the same general body type, as do we all. All of us in this room generally look the same as each other. 2 arms, 2 legs, head, hair, all of the same glands, all the same things. There's just variations on a theme between each and every one of us. Same thing here. By the way, these are pictures of what are called caymanolacutes. They are a completely fictional organism. These have never lived. Okay? But this is part of an exercise that I needed to do in my 1404 class that I took 15 years ago. Okay. There were actually 60 of these, and we had to cut them all apart and then put them in order of which evolved from which. I'm not going to make you do that in this class. I thought about it years ago when I was making this class. I decided not to. It's very time consuming and you tend to lose a lot of hair. So we won't do that. But you can tell that they all belong to the same general group but have enough unique physiology from each other that you can tell them distinctly apart, right? So all of these factors together make what we call index fossils. Are you all done with them? Or do you want, you're good? Okay. He's like, no, I'm not. I'm going to keep him. Okay, so some common index fossils. Things like ammonites and brachiopods. These are very common index fossils. There have been so many different variations of each of these. Each different variation works as a great index fossil. You'll learn more about both of these types of organisms later on in the class. Okay, isotopes. Let's talk about isotopes. Radiometric analysis. What is radiation? What is it? It's a good question. When I say radiation, everyone thinks nuclear weapons. Maybe you've watched that Chernobyl series, or you've seen, what's that show? U-571, something like that. An old nuclear submarine flick.
I mean, I watched Oppenheimer.
Oppenheimer, yeah. Oppenheimer was great. Okay. The whole thing with radiometric analysis comes down to isotopes. Now, an isotope is a variation on an atom that has gained or lost neutrons in its nucleus. This changes something about it. Do you remember what has changed? There were a couple of numbers that are unique to each element that we talked about. We talked about the atomic number. What determines the atomic number? Number of protons. Yeah, the number of protons in the nucleus. The column that they are in, dictated by what? The number of electrons in the valence shell, the outermost shell. And then there was the atomic mass. That is how much mass is within your nucleus for the most part. Most of the mass is in the nucleus, which is made up of protons and neutrons. So if I change the number of neutrons on my element, what changes? The mass, thank you. Good. So an isotope is a variation on an element, on an atom specifically, okay, that has either gained or lost neutrons, changing its mass. Now, some of them are totally fine with that. Okay, things like carbon, for the most part, totally stable. Carbon-12, carbon-13, carbon-14, all three of these exist. Carbon-12 is the normal version. Carbon-13 is slightly heavier. It has a little bit more mass. It's got that extra neutron in its nucleus. Carbon-14 has 2 extra neutrons. Carbon-14 is interesting because carbon-14 is only made when you burn fossil fuels. Yeah, interesting, huh? So, we've seen the ratio of carbon-14 in our natural environment absolutely skyrocket, right? I don't have the chart here. I could show you. It's literally like, whoop, like the worst hockey puck graph chart you've ever seen in your life, okay? Because of the quantity of carbon-14 that we are generating. Most of the carbon dioxide we generate as a result of the fossil fuel consumption is carbon-14. Now, there was some in the environment before we started burning fossil fuels from things like, wildfires. And every now and then a lightning strike might light a coal bed on fire, things like that. So there was always just a little bit. But since we started the Industrial Revolution, it's just way up there, okay? So that's carbon. Stable, for the most part. They don't mind. They aren't radioactive. But then there are the unstable elements, things like uranium. Uranium normally is number 238 on our periodic table of elements. But to make the radioactive uranium that we use in things like bombs and reactors, you make uranium-235. It has lost 3 neutrons, making it unstable to the point that it starts blasting particles off of itself, electrons and protons and neutrons, blasting them out in every direction it can to try and reach stability. And eventually it does, given enough time. All this uranium-235 degrades, decomposes, decays is the word we use, decay. It decays to a new stable isotope of lead. Uranium will eventually become lead, but that takes time. How much time? This is where things called half-lives come into play. A half-life is the amount of time it takes for a half of any volume of an radioactive and unstable isotope to decay to its daughter isotope, its stable daughter isotope. So for uranium-235, it becomes lead-207 over however many half-lives, depending on how much of it you've got. So here's an example. Here I have a dinner plate filled with delicious uranium-235. Who wants a snack? It kind of looks like a chocolate chip cookie. I'm so sorry that everything in my class always comes down to cookies. Okay? But it's meant to be a plate filled with uranium-235. Okay? I have a certain quantity of it. After 1 half-life, how much of it will still be uranium? No, not none of it. Although that is a cool province in Canada I'd love to go to someday. After 1 half-life, how much uranium will I have? Half, thank you. That's what the half-life means. It's the amount of time it takes for half of my volume to decay to a daughter isotope. So after 1 half-life, I will have half and half, uranium and lead. Now in the case of uranium, that's 703 million years. Okay? So after 703 million years, half of my uranium will have become lead. Now how does this help me? Well, if I have an object, say granite, it probably has at least some small quantity of uranium in it. And no matter how much uranium it has in it, I can find a half-life on it. How do I find that half-life? I find the ratio of uranium-235 to lead-207. And then that tells me how many half-lives have passed. If I have a 50-50 ratio, I know that that rock is 703 million years old, or around there. But what if it's like a 75-25 ratio? How many half-lives have passed? If it's 75, if the ratio of lead is 75% to 25% uranium, how many half-lives have passed? 2. How many times can I divide something in half? Infinitely. You can divide any quantity of anything in half infinitely, right? So after 1 half-life, it's 703 million years old. After 2 half-lives, I've got a 75 to 25 ratio because I've divided 50 in half. And then after 3 half-lives, I've divided 25 in half to 12 and a half. And then after 4 half-lives, I've divided 12 and a half in half to 6.25. I was like, whatever that is, right? 6.25. So I can keep dividing it in half and figuring out how old things are. And this, my friends, is radiometric dating. This is how we know exactly by year how old things are. People often refer to this as carbon dating. Have you heard that term before? It's not actually accurate. Carbon dating uses the ratio of carbons and how far along the carbon-14 and things have degraded. That's useful up to, we don't really use that past 50,000 years because it gets really unreliable. Anything older than that, which is the vast majority of geologic time, we use radiometric dating, radioactive elements. Okay? The actual name for this is in situ laser ablation multi-collectively coupled plasma mass spectrometry. You can see why we just call it radiometric dating, right? Okay. All right, so what do we know about Earth through radiometric dating? The oldest rock on Earth is 4.3 billion years old. This is found in the Acosta Gneiss in Australia. This is actually the crystal that age came from. This is a 4.3 billion year old crystal of zircon. However, that's not the age we tell people. That's not the age that I told you the Earth was. I told you it was 4.543 billion years old. How do we know that's how old the Earth is? Well, because that's how old the moon is. The oldest rock that we've recovered from the moon is 4.543 billion years old. So how does that relate to Earth? Well, the moon was formed when another planet, early on in Earth's formation, as our solar system was still figuring itself out, so to speak, another planet, there were many other planets in our solar system. We're down to 8 now. There were way more to begin with. A bunch of them probably got sucked in and absorbed by Jupiter and Saturn. A couple of the other ones impacted other planets. One of them, named Theia, hit Earth. It was about a Mars-sized planetoid that ran into Earth. Our orbits collided with each other, much in the similar way that that Apophis asteroid I mentioned earlier might. Okay? They ran into each other. Their masses combined together to make the Earth that we have and love today. But some of the debris from this impact got blasted off, got stuck in the orbit, and resolved itself into our moon. We probably didn't have a moon before that, or at least we did. If we did, there's no evidence of it anymore. But we have one now as a result of this impact, which happened at least 4.543 billion years old, billion years ago. So it's entirely possible we could find a rock on the moon in the future that is 4.6 billion years old, and then we would push the date of how old the Earth can be to 4.6. Maybe it's 5. Maybe it's 5.1. Exciting things. On that note, some exciting research about the moon has come up lately. A Chinese probe returned from the moon a couple of years back. I believe it was fall 2023. Called Chang'e 5. The Chang'e 5 probe came back with rocks from the moon that they dated to be 2 billion years old. Which is kind of interesting because the moon is a small enough body that was formed through impact material, not through the normal planetary creation process, that we assumed it cooled off really quickly after this impact. It formed, it cooled off, it's just been a cold bowl of rock ever since. But this rock that they brought back, that the Chinese probe brought back, is from a lava flow that's only 2 billion years old, it turns out. Which means that for more than 2 billion years, the moon had flowing lava on the surface. Why? How? How is it possible that something that small could stay hot inside that long enough to have volcanic activity on the surface? And how cool is it to think that if you were standing on the Earth 2 billion years ago, looking up at the moon, you could see little lava flows, little red lines across the surface of the moon. Isn't that interesting to think about? Questions that we're still trying to answer. Very fascinating. So let's finish up, well, not finish up, but let's continue with a conversation about science and how science works. We use the scientific method. The scientific method basically states we make an observation, okay? Diego's wearing an OCA 25 shirt. That's my observation. Now, I could make a couple of hypotheses based on that. If I had absolutely no information whatsoever about what OCA is, I could assume OCA is an organization that is 25 years old. I could also assume Diego is part of some organization or school that has some important thing going on in the year 2025. These are a couple of very valid observations I could make. How would I go about testing this hypothesis? Well, I could ask him questions. I could do some research, figure out what is OCA exactly, and why is the number 25 so significant? We are in the year 2025. There may be a corroboration there. I can do all sorts of things to test both of those hypotheses. But in the end, I would find out that one is wrong and one is right. The one that is wrong is the one that doesn't survive the testing process. The one that is right is the one that does survive. However, here's the trick. It's very rare in real science. In this example, right, I would absolutely find out that he's wearing that shirt because he goes to a school called OCA and he's graduating in 2025, right? That's what I would find out. But in real science, it's very rare to come down to an absolutely 100% this is the answer solution. Instead, it is far more likely that we simply fail to prove a hypothesis wrong. This is the trick with science. If you just try to prove yourself right, you're almost always going to do it because you've already made up your mind you are. But if you're trying to prove yourself wrong, that's where the real science lies. Because in trying to prove yourself wrong, you're doing your best to figure out what the truth really is. Science is all about truth no matter what they say. Who is this they I'm talking about? Politicians like taking truth and circumventing it for themselves. They like taking science and doing the same thing. There are many scientists who would contend that science isn't about truth at all. I believe that science is all about truth. Okay? And to find the truth, you need to try and prove yourself wrong instead of try to prove yourself right. Because that's how we get there. Okay? This is the scientific method. Now, after your hypothesis has survived the testing phase, you failed to prove it wrong, you have a theory. It is a working theory. That's where theories come from. Any questions about the scientific method? Okay. So let's do a quick run through of the rock cycle. The rock cycle, I like to start off when we talk about magma. Magma is melted rock. Rock that has been heated so high that all the minerals, or most of the minerals, have reached a state where they have to be in liquid form. There's too much energy in the system. They cannot remain as a solid crystalline network. Therefore, they melt, just like your chocolate when you leave it out in the sun, right? And then it cools off. It recrystallizes into... What type of rock comes from magma? Mafic is a kind of... Huh? These are all words that describe properties for... Huh? These are all words that describe igneous rocks. Good. Yeah, I was looking for the general broad category of rocks. Igneous rocks come from magma. That's the only source that igneous rocks can come from. They don't come from anything else, okay? That igneous rock is exposed at the surface. It is subjected to things like weathering and erosion, and it gets washed away, and it gets deposited, and through diagenesis, it becomes sedimentary rock. Your sediment becomes sedimentary rock. Good. That sedimentary rock gets buried deep underground. It gets crushed. It gets pressed. It gets heated until it goes through a process and becomes... These are all made out of minerals. I'll give you a hint. It goes through a process called metamorphosis and becomes metamorphic rock. Oh, camera lost me here. Camera. Hello. Right here. Camera. Stay with me. Did I accidentally zoom it in? Is that why? Hold on. Let me check this. How about now? There we go. Okay. So, we got metamorphic rock. This metamorphic rock gets buried deeper and deeper and deeper and gets so hot until finally the melting point is passed and we get magma. Remember, lava is what we call it on the surface. Magma is what we call it underground. Okay? But you were right. Okay? So, this is your rock cycle in a nutshell. And, you can skip a few steps. You can jump to a different part of the rock cycle. Sedimentary rock can get rebroken down into sediment. It doesn't have to get buried and become metamorphic. Things like that. But there are other things that you can't skip. Like igneous rock only comes from magma, right? Okay. So, layers of rock are distinguishable from each other based on a few things, right? We talked about how to differentiate minerals from each other. We talked about how to differentiate rocks from each other. But layers themselves also have their own distinct names. Not like classification, so to speak, but we do have a system for classifying them based upon size and the way that they're grouped together. Okay, so the first thing you need to know: formations. That's kind of your initial one. When you hear about some layer of rock, you'll usually hear it referred to as a formation. The Hell Creek Formation is very famous for having a lot of Tyrannosaur fossils in it. Okay. Formation. A formation has within it members. So you could have a member of the Hell Creek Formation. Okay. Formations themselves are part of groups. Groups are part of supergroups. Now, why do we do this? Well, let's say that my formation represents a single transgressive period. Okay? Transgressive meaning ocean levels rising. Okay? And there's evidence of that in this layer of rock, and that's why I have distinguished it from the rest of the layers of rock by calling it its own formation. Okay? So this is a formation. Let's call it a sandstone. Okay? This member is a smaller unit inside of that. Perhaps there was a heavier silty component, whereas the rest of this is still pretty sandy. So this is the salty part of it, or the silty part of it, but still part of the formation itself. So that would be that member. Okay? Small change within the larger unit. And on that same note, this formation is part of this group. If this represents a single transgressive sequence, perhaps I have layered these groups together. I've put all the formations within the same group to show transgressive and regressive. A pairing. Or maybe transgressive, regressive, transgressive, regressive, transgressive, regressive. A whole sequence of them within this group to show that they are all related to each other by the rising and falling of sea level during that time. The supergroup may represent all of those sequences within, say, the entire Triassic. So we group them away from each other, or apart from each other, based upon their relativity to each other. Right? Following along with this? It all has to do with the order of sequences, basically. This is a big part of that, that thing I mentioned before called stratigraphy, which you will become very familiar with. That's the first lab you're getting, actually. Your second lab is a stratigraphic exercise. It has everything to do with the way that the layers are related to each other and how you can interpret it. Earth is pretty cool. It's a unique place. If we do the math, based upon how large our universe is and how many planets we have seen in the area that we can observe, there are an estimated, what number is this? 100,000 million, billion, trillion, quadrillion, 700 pentillion planets in our universe. Now, even if there is a 1 in 1 trillion chance that life exists on one of those planets, those are still really good odds, right? Where is a trillion here? 100,000, million, billion, trillion. That's still a 700 million planets in the universe that have life on them. 1 in a trillion sounds almost impossible, and yet based on these numbers, it's still really likely. Interesting. Now, there's a whole bunch of other things to think about. The fact that the building blocks for life on our planet are based upon just a few amino acids. You guys know what adenine is? Have you ever taken biology or organic chemistry? Adenine triphosphate, does that sound familiar at all?
Like
ATP, yeah. Yes, something about energy indeed. ATP is the amino acid chain inside of all of our cells and inside the cells of every living thing on this planet. All of our life here is based on DNA, and all of that DNA-based life requires ATP to store energy. Guess what? We see adenine in space. We can see it looking back at us, reflecting back at us. It's just hanging out in space. It is an incredibly common amino acid. And there are some experiments that have been conducted in labs where all you do is you combine a few inorganic ingredients, a few gases, a little bit of water, maybe some methane, which is also extremely common in space, right? And you just put a little electric charge in there, and boom, all of the amino acids necessary for organic molecules. Those organic molecules made life here. All of these ingredients, extremely common, hanging out in space in clouds. So what do you think the likelihood is that this is the only planet in our universe, or even only 1 in a trillion odds, that all of those basic, very common inorganic stuff didn't come together on a planet or many planets around our universe and form some kind of life? Does it all have to be DNA-based? No. But we know that the circumstances that made life here cannot be uncommon, because everything that was required for it to happen here is extremely common, just hanging out in space. You get a little bit of this, a little bit of that, a smidge of this, and a lightning bolt. And you've got organic molecules, which go on to make amino acids. These amino acids make chains. Those chains make proteins. And before you know it, you've got the first bacteria. We'll talk way more about that in coming days. But my point is here, there are some things that make Earth very unique. We have an atmosphere. We have so much water. We have soil for things to grow. But the things that make Earth so unique and sustainable for our life are probably present in many other places too. There are, I want to say, just off the top of my head, just using our telescopes, 26 other planets within our neighborhood. And now when I say neighborhood, I mean like within the 30 light years around us that we can see pretty clearly with our telescopes. I believe there are 26 planets that have atmosphere. We can see that there's water reflecting off the surface. And they're close enough to their stars to be hot enough as Earth. At least 26 planets, Earth-like planets. Some of them are smaller, some of them are bigger. Some of them have more gravity, some of them have less. Some of them are a little bit colder, some of them are a little bit hotter. But within that band of life as we call it, the Goldilocks zone around their stars, they could be just as hospitable as Earth is. Maybe we'll know one day. But for now, yeah, there may be life in other places, and I personally believe that there absolutely is. I think that there's a lot of it. There are certain issues about why we haven't seen it yet. The Fermi paradox is fun. The Fermi paradox basically suggests if there is life out there, why haven't we seen it yet? Right? And bear with me, if we say, just based off of human civilization, that it took humans about 20,000 years to go from building up their own societies to colonizing somewhere else across the ocean, right? It took about 20,000 years, as far as we can tell, for human civilization to go from Africa to Europe. And then from Europe, about another 20,000 years, to start expanding other places, Iceland, Greenland, eventually the Americas, right? Polynesia, way far out in Indonesia, right? About 20,000 years for a community to grow up to the point where it could go colonize somewhere else. If we use that same statistic and we say that from when all of humanity was generally established, it took 20,000 years for us to say go to our moon. And then we extrapolate out from there and we say if we ever send a colony ship to another planet. Let's say we send a colony ship to our nearest neighbor, about 4.5 light years away, traveling at 10% the speed of light. If we really put all the resources together, we could make a starship that can travel at about 10% the speed of light. Okay? It would take how long to reach that planet? Going at 10% the speed of light, and it's 4.5 light years away.
40 years?
45. Yeah, you were talking about a 45-year trip, right? Those people ain't coming back, right? That's a 90-year round trip. That ain't happening, right? So you send a ship out there 45 years away. It takes them, let's call it another 20,000 years. Now, why do I say 20,000 years? These people are showing up with one spaceship, right? If we send 40 people or 100 people or 1,000 people on the ship, you will never be able to send them with enough resources that they will make an Earth-like civilization right off the bat. They're starting by plowing fields, planting seeds, building log cabins. They're starting at ground zero. They don't have their own spaceships. That spaceship probably falls apart in the first or second generation and is unusable. And by the time we're talking 12 or 13 generations, the fact that they ever arrived on that planet in a spaceship is probably a myth, right? So we're talking about another 20,000 years for that group, that colony, to reach the point where they can in turn colonize. I'm being very generous with my time here. It's probably less than that, but I'm being very generous with my time to make a point. Going at this rate, if we today were to start colonizing out, and every 20,000 years, each of those colonies sends out another colony, we start branching out and we start building humanity through our galaxy, we would be able to colonize the entirety of our galaxy in 300 million years. Humans all throughout the galaxy in 300 million years. Our galaxy is way older than that. We're talking, gosh, 6 or 7 billion years old, maybe. Our universe is 14 billion years old, right? Our galaxy itself, 6 or 7 billion years old, maybe. So if it would take humanity, generously speaking, 300 million years to populate our galaxy, why hasn't anyone else done it? And that's the Fermi paradox. The most common answers to that are, well, all intelligent civilizations are doomed to destroy themselves.
Maybe they already did.
And that's the argument.
Maybe
Oh.
we're a part of the.
Oh, that's another fun one. That's another fun one. What if we are a colony and we don't know it?
Yep.
Right? There's no evidence to suggest that, but it's a fun idea. What if we are one of those colonies and it's our destiny to, in however many years, maybe it's been 20,000 years, right? And now we are getting ready to continue that effort. But the more common ideas are that intelligent civilizations are doomed to annihilate themselves before they reach the point where they can expand throughout the entire galaxy. And then there's the other idea of that intelligent civilizations ultimately reach what is called a singularity. You ever heard that term before? A singularity it's a term that has multiple meanings, but in this context, it means they ascend beyond the material plane, where our intelligence reaches a point, or perhaps our knowledge of technology reaches a point where we figure out how to transform our lives out of the material and into, I suppose you could think of it as the energy state, or another dimension, where we figure out how to leave this one behind. That's another interesting theory. There are lots of cool things here, but the Fermi paradox basically says, if there is intelligent life out there, why hasn't it come to say hello? Why don't we see evidence of it everywhere? Why don't we have radio signals? If there is any universal language, it would be radio, right? The stars speak with radio. They emit radio waves constantly. We know how to make them to communicate. Any spacefaring civilization would know how to use radio to communicate, and we have gotten nothing. Yeah.
Is that why we sent Voyager 1 in space?
Yeah, the Voyager series drones were sent in space, bearing gold plaques that have very basic art on them demonstrating humans and the fact that we are here and that we want to talk. And I believe it left the outer reaches of our solar system,
2012.
yeah, in 2012. We can't see it anymore. It's passed beyond our ability to communicate with it or see it really. For all we know, it could have left our solar system. Here's the thing. Our solar system is surrounded by what's called the Van Halen belt. Van Halen? No, Van Allen belt. I like Van Halen. Yeah, the Van Halen belt. No, the Van Allen belt, which protects our solar system from a lot of the galactic radiation that we receive, or that we would receive. So we don't even know if that probe survived the transit. We hope it did, but if it did, it's floating between solar systems now, just out in the dark of our galaxy. But its whole purpose was to introduce ourselves to other civilizations if they do exist out there. So yeah, this is the state of affairs. Life, extremely likely. Intelligent life, the Fermi paradox may suggest not so much. But life, absolutely. Interesting, huh?
Very,
Very good.
very cool.
Yeah, very cool. And that sets the stage for 1404. We're going to be talking about cool stuff like that this whole time. It's going to be awesome. I love talking about this sort of thing, in case you can't tell. All right, any questions for me before we end for the day? No? All righty. Well, that's where we will call it. There is no lab today. I will assign your lab on Monday, the next time we meet. Monday. We meet Monday, Wednesday. Today is Wednesday.
Wait, no. Yes, today is Wednesday.
Today is Wednesday. We meet Monday, Wednesday.
Hey, was this also lecture 1 notes?
Say what?
Lecture 1?
Yes, this was lecture 1.
Oh, okay.
Yeah.